Hello, my name is Errol Bartran and I'm presenting alongside John Armour, Nicole Finley, Robert Long, and Jesse Rocky. We are a part of the IDX Mass Timber Group here at Washington State University, and we're looking to develop a pilot supply chain for manufacture of CLT in the Pacific Northwest. So some goals that we have are to help the people, the environment, as well as the built environment. So it could help the environment by removing damaged trees from the forest. This damage could come from beetle kill, fire, or other things. In addition, there have been economic downturns in several rural areas in Washington due to the diminishing lumber industries. CLT would create a new market for that lumber and help turn around some of these local economies in the Pacific Northwest. Also, wood has been limited in its capabilities in going tall due to fire restrictions and other concerns. CLT has some unique properties that will allow it to overcome some of these challenges. So we're very excited about the prospect. In our previous presentation, and you might not have seen that one, we kind of discussed what is cross-laminated timber. It's essentially a wood panel that is similar to plywood. It's a dimension lumber where the grain in each layer is crossed. So the grain is perpendicular to each other between the layers. And the number of layers can vary depending on structural need. Also in the previous presentation, we covered some of the natural capital, in the Pacific Northwest in this four-state region of Washington, Oregon, Idaho, and Montana. We looked at what areas have been affected by fire, by beetle kill, and where the forests are. How dense are they? What type of species are there? Just everything. And as you can see, two areas that we noted that were of particular interest are eastern Washington and Idaho, as well as the western Oregon region. We also looked at physical capital. So as you'll see here, there's a lot of information on this slide. There are 3 locations in yellow. Those are the locations of industry partners that we will look at more later in this presentation. But then also notice that the red shows kind of the population centers. So Seattle clearly dominates this area, with Portland coming in a distant second. And then also we've got all this transportation infrastructure, including railways and roads connecting the region, which we'll need to take advantage of in order to make CLT a viable product. So for this presentation, we're going to look a little further into that geospatial analysis of the four-state region. And then after that, we're going to look at characterizing some of the baseline buildings, be it warehouse, multifamily, mid-rise, high-rise, large office. And we want to look at what are the material requirements for those and some specific loading and other concerns for each of those buildings. Okay, for the geospatial analysis, there are 2 main pathways that kind of intersect and then create the final product. So at the top, that top process, we have the transportation infrastructure, and then we look at what areas can be reached from each of those 3 mill locations. We do this both by time and by distance. For simplicity, I just did the time analysis on this slide. Down below, you can see the forest cover for the four-state region. To the right of that, you'll notice that that forest cover has been greatly diminished. The reason is that on the right side, we clip to only Forest Service land that can be harvested. This does not include areas like wilderness areas. The reason behind this is that the Forest Service provide a large amount of the funding for this project. So then when we have those 2, we clip the Forest Service working ground that can be harvested to those regions that can be reached. And then on the far right, you get the area that can be reached and can be harvested for each mill. As you can see here, these are 3 industry partners located in Forks, Darrington, and Colville. And this is the distance analysis. And I kept that in orange so for simplicity in this presentation. As you can see, the darker regions can be reached within 25 miles of each location, and then you go out to a 50-mile radius, so to speak, and a 75-mile radius. So this kind of shows you what can be reached from each location, as well as some forest cover to kind of give you some perspective. And then we clipped specifically to Forest Service ground. So you can see in the dark green, that is harvestable Forest Service ground within a 75-mile reach of each location. Then we did the same thing for time. We got the polygons the same way. Notice that these shapes are a little bit more stretched out. The reason is that roads have different speed limits, so you can travel, the amount of distance you can cover varies more by what road type it is. As you can see here where it branches out, that is the faster speed limit roads. Then we did the same thing. We clipped it to what Forest Service ground can be harvested within a 90-minute drive time of each location. Another thing I want to look at is some market analysis that was done. This shows construction of office and multifamily in the Pacific Northwest from 1980 to the present. And as you can see, once again, Seattle clearly dominates the area, Portland coming in second, but we want to focus on Seattle for the reasons as you can see in this graphic here. So what's going on in Seattle? As we can see throughout the Pacific Northwest, there is growth in several building types, and a lot of that is going to be going on in the Seattle area. So what is going on in the Seattle area? This is specifically the downtown South Lake Union area of Seattle, and you can see construction projects based on what type, office or multifamily, as well as material needs. So clearly there's a lot going on, and a novel building material like CLT stands to make a large difference in this area. Now I'd like to hand off this presentation to John, and he will discuss how different building types are defined.
So before we can start talking about defining all of our different building types for this project, we need to look at how different organizations define building types. So here I have a list of the IBC, LEED, Seattle Government, and Pacific Northwest Energy. But this is kind of confusing. Every organization designs them slightly different. So in an effort to stop that confusion, we've created this graphic. So here you can see the IBC, and they have a threshold at 75 feet. Anything below 75 feet is considered a low rise, or everything above 75 feet is considered a high rise. And this has to do with fire. There's a fire truck in this image, and that's the maximum height for the fire truck ladder is 75 feet, and that's why they make that break there. If you look at LEED and Seattle Gov, we have 1 to 3 stories is a low rise, 4 to 8 stories is a mid rise, and 9 or more stories is a high rise. If you look at Pacific Northwest Energy, we have 1 to 3 stories is a low rise, 4 to 6 stories is a mid rise, and 7 or more stories is a high rise. For our presentation and for the rest of this project, we're going to be considering the Seattle.gov version, and that's because we're looking at our baseline for in the Seattle area. So we chose to have 1 to 3 stories as a low rise, 4 to 8 as a mid rise, and 9 or more stories as a high rise. So now to get started developing our baseline for warehouses, we noticed 2 big trends when we first started to look into warehouses. The first trend is that across the United States, warehouses aren't being refurbished anymore, but they're actually being torn down and rebuilt. And this is one of the reasons that we chose warehouses, because there's a lot of warehouses being built right now. And so there's a lot of opportunity for CLT to be a warehouse building material. The other thing we noticed is, like I was saying earlier, that we're looking at the Seattle area. And when we started looking in the Seattle area about the current warehouses that are there, we noticed that there was a big size discrepancy. There's really big warehouses and there's relatively smaller warehouses. And what we came up with is that warehouses in more of an urban setting, like the industrial district here that we have highlighted on the map, they're smaller warehouses. And that's because they have restrictions like block size, and the general cost of land in an urban setting is a lot more expensive. And then if you look in more of the Kent area, which is in the lower part highlighted, warehouses get a lot larger, and that's because they don't have those same kind of restrictions like block size and relatively expensive cost of land. So when we start looking at more of the construction, so what we ended up defining our warehouses to be is We defined the small warehouse to be 280 by 147 feet, and our large warehouse to be 630 by 294 feet. And we compared this to a football field here. The small warehouse is about 1 football field, where the large warehouse is about 4 football fields. And for the height of both warehouses, we're making it 40 feet tall. And that's because there's been a new trend recently that warehouses are getting taller, and that's because they're getting more automated. And by automated, I mean robotics are doing a lot of the work inside the warehouses, and so they can access really tall shelving systems, and it's not an issue. And so that's the reason for that 40-foot height. When we started to take a look more at the structural components of the warehouse, we realized that one of the big defining factors on how the day-to-day operations of a warehouse is where the column spacing is compared to the racks. And so we chose a very average rack size of a rack depth of 3.5 feet, a flue width of 2 feet, and an aisle width of 12 feet. And based on this equation here, it gave us an optimal column spacing of 21 feet. And so we wanted to put our columns at that spacing. Another important part about when, developing the layout for a warehouse is we want to make sure that we're using materials efficiently. So we're going to build our roof out of CLT panels and 3-ply CLT panels. And so we looked at what the maximum span for those 3-ply CLT panels are with our roof loads on them. And we determined that it was just over 21 feet, which led us to create this general layout. This layout here is for both the large and small warehouse, but specifically this one is the small warehouse. The large one is just on a bigger scale. So we're spanning columns at 21 feet here, and we're having a glue lamp beam span at 35 feet between each column. And then we're going to lay up our CLT panels from beam to beam on that layout. So that's our general floor layout. Here's a 3D rendering of our small warehouse, and what we're going to do for this is we had 5-ply CLT panels for all the walls and 3-ply CLT panels for the roofing. We took out a wall here so you can see the interior of the building. You can see all the columns and beams, and we're going to use glue lam for that. Something you'll notice about this building is that there's no lateral bracing, and this is true for both the large and small warehouse. And that's an assumption that we made based on our wind load calcs because the CLT panels are really strong in in-plane shear. The total volume it would take to create this small CLT warehouse would be 960 meters cubed, and the total volume of CLT it would take to create the larger warehouse would be 3,000 meters cubed. So now I'm going to hand it over to Nicole, and she's going to talk about some of the general assumptions that we use in developing the rest of the buildings for this, as well as she's going to start talking about our definition for mid-rise.
So as mentioned previously in this presentation, we are looking to determine the total volume of CLT needed for each of these different baseline buildings. So to do that, it's important to note some of the general assumptions that went into developing these baseline buildings, specifically the mid-rise multifamily, mid-rise high-rise, and large office building. In order to analyze these buildings, we considered gravity loads only. That being said, we did not consider lateral loading or the effect of fire. We assumed that gravity loads without a live load reduction would give us a conservative estimate for the volume of CLT demand for each of these buildings. As you can see here, the vertical CLT member you see is analyzed as a column, as a wall. The horizontal member you see here would be a floor, analyzed as a bending member. This slide illustrates some of the common gravity loadings we have used to analyze our buildings. You see here the 9, 7, 5, and 3-ply CLT members, as well as their corresponding pounds per square feet. Some common building materials we used were concrete, insulation, roofing, as well as it's important to note that we assumed a mechanical loading of 2 pounds per square foot per floor and a partition wall loading of 5 pounds per square foot per each floor. That being said, it's important to get into the mid-rise building definition. So here we have the Seattle zoning requirements for a mid-rise multifamily building. This building was looking to compare the Type 5 over Type 2 building that you see in the Seattle market. It's growing and appears to be a good replacement for the CLT material. That being said, this building usually hits between 60 and 75 feet. So the multifamily mid-rise building Seattle code requires that these buildings hit a capacity of 60 feet or in some mid-rise 85-foot zones at 85 feet. The width of these buildings are limited to 150 feet, and so this zoning requirement that you see here was used to illustrate our multifamily mid-rise building. As mentioned, we are looking to compare the Type 5 over Type 2 building. That building is light frame timber construction over concrete construction. We're looking to replace this building with a Type 1 over Type 2 building, being CLT as a non-combustible material over a Type 2 material, again, which is that concrete. Again, it's noted that 5 or type 2 is limited to about 75 feet. This is due to the coating restrictions on light frame timber. So that 5-story limit on light frame timber is going to limit this building to about 75 feet, which doesn't use the full capacity of that mid-rise 85-foot zone. So instead, we use 7 floors of CLT over 1 concrete podium. The CLT floors would be floor-to-floor heights of about 9 feet 4 inches, and that concrete podium would be about 15 feet floor-to-floor height. This puts us right at that capacity of the mid-rise 85-foot limit. Going into the deeper analysis of this building, we start to develop a floor plan. So first we looked at the slabs, and through our analysis, we determined that a 5-ply member could span about 16 feet with vibration governing. That being said, the next step was to look at shipping and feasibility of getting that span length onto site. We realized that shipping lengths usually standardize about 48 feet before going into the complications of overhaul shipping. That being said, we wanted spans that evenly went into that 48-foot limit, so 16 was an adequate span length. Next thing was to check that our walls could handle the tributary length for the loading coming down on them. We analyzed different members, 3-ply and 5-ply. A 3-ply was determined to support about 34,000 pounds per foot width. This is including a column reduction factor of about 0.6. That being said, the demand on the second floor, so having the greatest demand for our CLT there, was about 7,500 pounds. So the 3-ply was clearly adequate for all floors. That being said, again, we didn't include fire in our analysis, so it is noted that later this may bump up to a 5-ply with deeper analysis. Finally, we have our 3D rendering of the multifamily mid-rise building. Exterior walls and roofing are excluded in order to allow you to get a deeper visual of the bearing walls and floors that you see here. It's important to note specifically some of these side values that we see over here that illustrates some of the specifics of this building. Most notable is the demand CLT. We have a total volume of about 93,000 feet cubed, as well as 2,400 meters cubed. These values will be compared to the other baseline buildings that you see later in the presentation. And now I'd like to hand it over to Rob, who will discuss the high-rise building.
Over the last 30 years, we've seen significant increase in the building and the construction of high-rise multifamily buildings. In the early 80s, only about 0.1% of these buildings made up the total market. Now we see that multifamily high-rises, they make up close to 5%. So this is important information for us to know because it shows a promising future for the construction of a high-rise multifamily. The Seattle zoning code told us that in the Seattle area, these buildings had a max tower height of anywhere between 37 and 160 feet. There are certain areas of Seattle that allow this tower height to go up to 240, but looking in the South Lake Union zone, we saw that for multifamily high-rise buildings, they had a max height of 160 feet. So because of that, this was the total height that we were designing our building with, as well as we saw through more market analysis that the overall envelope and square footage for these buildings was not to exceed 10,700 square feet. So we wanted to optimize this and make it as large that number as possible, the 10,700 square feet, which leads me into our floor plan design for this high-rise multifamily. Here you can see that we have 10 family units, 5 on each side, separated by an 8-foot corridor. The dimensions of this each unit is 40 feet by 24 feet, giving an overall dimension of 88 feet in the width and in the length 120 feet. This gave us an overall dimension of 10,560 square feet, which got us really close to that 10,700 mark we were shooting for, which would, the reason why we want this maximum amount is just to give an overall maximum amount of CLT that might be used for one of these buildings. But as Nicole mentioned, there's a 16-foot governing factor due to vibration. Vibration didn't allow us to have spans greater than 16 feet. Because of this, we have to use composite action. What composite action is it pretty much utilizes the material of concrete and wood. Here we have 3 inches of concrete over a 5-ply CLT panel. As we know, concrete is best when it's in compression. Its strengths and properties when it's in tension aren't that great. And likewise for CLT or wood, the strengths of it are when it's in tension because it avoids issues of buckling. So because of that, we're now utilizing the compressive strength of concrete and the tensile force and strength of the wood, which allows us to get the 24-foot spans as you saw in the floor plan before. Here we have a 3D model, 3D rendering of this building. As you can see, we have 15 stories, which have a height of 156.4 feet, getting us really close to that 160-foot mark, again, maximizing and optimizing the total amount of CLT that is going to be needed for these types of buildings for comparison in the future. The total floor area, as I said before, is 10,560 square feet. The total volume of CLT for this is 140,000 feet cubed, or in meters cubed, that would be 4,000 for the total volume. So next, now that we've talked about multifamily high-rise and mid-rise, I'm going to hand it over to Jesse, who's going to talk about office buildings.
Hello everybody, my name is Jesse, and today I'll be sharing with you my large office design model. So this model is based off the mixed-use zoning requirements in the South Lake Union region of Seattle, specifically the SM 240 region down here in the blue. What's unique about this area is that it's what's known as an urban center, so we're able to build higher buildings here as long as we can share the space with other building types. These urban centers are fairly common in growing cities like Seattle, and they're designed for this larger building height for a denser area so that it can accommodate a growing economy and a large population boom. So here in the SM 240 region, the specific region, we were able to build a commercial building to a height of 240 feet, which is a little higher than we normally would be able to build, but we then have to share that space with a 125 to 400 foot residential tower. Based on these requirements, it's not uncommon for us to, or it would not be unreasonable for us to design this model in association with one of the multifamily models that we saw in the previous slides for this region. And so that's an advantage that we have there. Here's a typical floor plan of the large office model. We see a 102-foot span by a 240-foot length. One of the important aspects to notice here is the core, the structural core, which handles most of the gravity loads. And then we have these shear walls here on the outsides that handle the major lateral loads. And those are fairly unique for the office because we don't have the partition walls from the multifamily buildings that kind of help control that lateral force. Another important thing to note is the spacing between the columns here, which is 24 feet, and that's our ideal panel length, as we explained earlier, because those panels are very easy to press, they're very easy to manufacture, and they're very easy to transport. So here we have a 3D model of the office structure. You'll see that it's 18 stories tall. 2 of those stories are in the concrete podium here, and then the other 16 are primarily CLT. And so we have a total height of 234 feet, which makes really good use of that 204-foot limit, or 240-foot limit, excuse me. So this concrete podium has a 15-foot floor-to-floor height, and then the CLT portion has a 12-foot 9-inch floor-to-floor height. The podium is primarily for lobby retail use, which is important in our zone, dining, loading docks and parking and things like that, whereas the upper portion, the CLT portion that we're concerned with, is primarily for office use. So something unique about this office design, because it's so tall, is that we need to really focus on the thickness of the CLT plies that we're using in the walls. And because it's such a tall structure, we get down even to the 9-ply thickness, which is over a foot thick, which is unique to this building. The other buildings, I think, only get to 5-ply or 7-ply. So for the design loads here, to accommodate the compounding self-weight of the floors, we have 3-ply in the top 7 floors, and then 5-ply, 7-ply, and 9-ply in the bottom floors. This, of course, affects the amount of CLT that we'll need and kind of cuts our efficiency as far as making the most out of the material for the building, for the floor area that we want to use. So now that we've kind of gone into detail of all these different structural types, we have, I was able to compile these images here for, I'm sorry, this slide is missing something. This is a comparison of all the structural types that we looked at, we're missing the small warehouse, which we kind of looked at earlier anyway, so that's okay. But we have the large warehouse, which is significantly larger than these other, the towers that we have covered. And the small warehouse as well is even larger area-wise than the large office, which I thought was interesting, but I'm sorry I couldn't share that with you on this diagram. So this part works. We have our total volume of CLT here. We calculated that for each building earlier, but I've compiled them here so that you can directly compare them. You'll notice that they're in cubic meters, which might be unusual to some of you. To put it in perspective, an Olympic-sized swimming pool is about 2,500 cubic meters. So for the mid-rise residential, for example, it would be about one swimming pool worth of just filled to the brim with CLT panels. So that kind of gives you an idea of how much wood we would actually need for something like the mid-rise residential. And for all of these structures, other than the small warehouse, we would need at least that amount to build them. And the reason why we're using the cubic meters is because CLT has been more popular in Europe and Canada for some time, whereas it's fairly new in the US, so we're still using the international units just to keep with the standard. You also see the volume to floor ratio for each building, which is pretty interesting and useful information because it shows us how effectively we've used the material. We see and how well we've optimized our space usage, because we have this is basically telling you the volume of CLT that we're using compared to the amount of floor area we're able to utilize with that same amount of CLT. So these numbers here, basically the lower they are, the better use of the space we're getting. And then that doesn't really apply for the warehouses because it's more of a rentable area or occupied area by residents or workers, and so it doesn't really take into account the storage, which is the primary use of the warehouses. So now that we have all this information from the structural analysis, where are we going to go with it? In our first presentation, we introduced you to the supply chain model, and basically it's all the steps required to get the raw supply, these trees and this harvestable lumber, converting it to CLT and then applying it to our construction sites and putting it into these buildings that we want to build. These are just the basic steps up here, and then I've included an example of how we might compile these, or kind of clump these steps into certain locations, so a mill or a factory. We showed you this, and then we showed you a lot of asset mapping in this first presentation, which we analyze these forests based on things such as the proximity, their ownership, the environmental impact we would have if we were to harvest from them. And so that was focused on this first part of the supply chain, the harvesting portion of the supply chain. And then today, we were looking at the site construction by analyzing these structures and seeing how much of the CLT we're actually going to need. The logical next step, therefore, would be to connect these two ends and really get into the meat here of this CLT production process. We can make an educated decision now based on this information we've learned on what kind of mills and factories we might potentially use to create this successful supply chain. And then after that, we're going to come back to these structures that we've analyzed today. Starting next year, early 2016, we're going to collaborate with the University of Washington, and we're going to revisit these models and get into the more advanced designs, some of the more advanced loads, and look into some of the stricter building codes, and really get these designs ready for real-world application. I've sent out a form along with this video. Professor Bayreuther sent it, and it allows you to send us any feedback or questions you might have. So that's an exciting future for us. At this point, I'd like to note that we have sent out a form along with this video. Professor Bayreuther sent it, and it allows you to send us any feedback or questions you might have. I highly encourage you to do so. We had a lot of information that we weren't able to include in this presentation. So if you have a particular question, it's very likely that we can answer that for you, and we will do so as promptly as possible. I'd like to thank you all for participating and watching us today, and for your continued interest in our program. We hope to see you soon, and have a great evening.